Hey there everybody, this is Mr. Piercy, and what we're going to be taking a look at in this video is something known as the chain rule. This is going to be an advanced derivative technique that is going to be really useful for finding the derivatives of what is going to be what we refer to in math as a composite function. Now, in our lessons, we've already seen the chain rule kind of popping up from here to there in some of our other earlier lessons. And in those instances, when I would look at the chain rule, let me go ahead and get my pen here set up the way I want it. Let's take a nice color here. We would look at it like this, where we would say that this is how we're showing the composite function for things that we're going to be taking the derivative of. And at the time, I had to show you what you would use for that, and we're going to see it again here shortly. So I'm not going to try to reinvent things that are already presented. But this is essentially what we're going to be doing in this lesson is trying to take the derivative of composite functions by something that is referred to as the chain rule. So here is kind of the notations that are typically acceptable for what they think of as the chain rule. So here, this is, again, what you've previously seen in some of your other lessons. And the way that I typically look at it is with this. This seems to be more familiar to students, more understandable than the notation that's above, where we say the derivative of y with respect to x is going to be equal to dy du times du dx. Now, the u term is going to be something that we'll be able to see at some point, because u substitution is going to be something that you inevitably do in calculus anyway. So there will be some examples that you'll see where we might do use some u substitution for our chain rule examples. But essentially, and that's what they would refer to as the Leibniz notation. But this is really what we're looking at here. This is what we need to understand, is to multiply the derivative of the inside function by the derivative of the outside function, or vice versa. Sometimes it may be easier to find the derivative of the inside first and then do the derivative of the outside. And that certainly follows with how you're trained to think about doing your normal order of operations. You kind of unpack them from the inside out, looking at things that are inside the parentheses and any exponents and whatnot. We're used to looking at things from the inside out. So whether we do it the way it's saying here, multiply the inside derivative by the outside, by the derivative of the whole thing, or vice versa, either way, it'll work out to be the same. Now, here's our first example, and it's a very simple example, which is intended to help us introduce how the chain rule is going to be worked. So let's take a look at doing it without the chain rule. So what we would do is we would take our function, f of x, and we're going to expand it using the notation that we have there. So I would have 5x plus 3 times 5x plus 3. And we'll do our normal distribution here and put it in standard form. And in this case, when I do, I would have 25x squared plus 30x plus 9. And now I can do the power rule for each individual term to identify the derivative, which in this case would be 50x plus 30. Nothing to it. Now, that one was intentionally not complicated. Okay, we can expand that one very easily, take the derivative of it, but it's a good stepping stone for how we're going to look at the function using our chain rule. So here we have same function, f of x is equal to parentheses 5x plus 3 quantity squared. So we're going to essentially, let me see if I can get my color coordination worked out. We're going to take the derivative of the outside function, the derivative of the whole thing. But we're also going to take the derivative of the inside piece, the 5x plus 3. So the derivative of the whole thing, using our power rule. And let me see if switching colors may slow things down a little bit. But hopefully, especially at the beginning, it'll help keep things straight. Okay, so the derivative of the whole thing, using our power rule, would just be 2 times 5x plus 3 to the first power, because we dropped the exponent value by 1 just like we normally do with the power rule. Well, now we're going to take the derivative of the inside part, which is the 5x plus 3. So the derivative of that is just 5. Now here we could stop if we were, just trying to give a numerical response to the function, but let's go ahead and simplify it. So I can take the 2 and the 5, and we'll go ahead and multiply those together because those are outside of the parentheses, which would give me 10 times 5x plus 3. And again, we could stop here perfectly fine, leaving it in factored form, but the idea is to show you that they're the same. So distributing the 10 puts me back at the 50x plus 30 that we got with our, when we distributed those two binomials and used the power rule. Okay, so that is essentially what the chain rule does. We take the derivative of the inside part and it'll get multiplied to the derivative of the whole function, and we wind up with this. Now this one kind of seems like it's actually going to be more work than distributing and using the power rule, but trust me, it's not going to be the same for a lot of our functions. So the chain rule, again, I kind of look at it like this: the derivative of the whole thing multiplied by the derivative of the inside, where this bit, the derivative of the whole thing multiplied by the derivative of the inside. So you can see, probably need to have parentheses around that. So let's go on here. Let's see what we can do. Now here, this would be a good introduction to what we would think of as U substitution. Okay, using Leibniz notation, we can look at this bit here and think of that as U. Okay, and I'm going to come back to that in a minute. But let's just identify what is the inside function. Well, the inside function is what I just called U there. That is the 4 minus x squared. And the outside function would just be the whole thing. It would be 4 minus x squared cubed, or the way that I've identified the inside part as U, I can look at it as U cubed. Okay. So what we want to do now is, again, find the derivative using the chain rule. So here we can say, let me go ahead and pick another color here. Here we're going to say f of x, the derivative will be the derivative of the inside part. So the derivative of this bit here is going to be, well, let's do it the other way around. Let's try and keep it uniform. Let's take the derivative of the whole thing. So the derivative of the whole thing, we'll look at this, and we'll just use the power rule. Look at it like if it was, what we would do here, we would just wind up with 3 u to the second power. So I'm going to wind up with this to be 3 times, oops, that is x, that's a 4, not an x. I always get so messed up when the variable is not first. Whenever they give me a number first, I always mess it up. X squared to the second power. And now we're going to take the derivative of the inside bit, which, we'll look at that one here. So the derivative of the inside bit, we're going to find now, well, the derivative of that is just going to be negative 2x to the first power. So anything that's not inside the parentheses, we're going to go ahead and multiply those together the way that we would, normally do. So let's just kind of go back to finishing this. All right, so this 3 and the negative 2x, they can get multiplied together, and it would be negative 6x times 4 minus x squared, quantity squared. And this is what we would probably stop at, because there's no reason to distribute the 4 minus x squared bit and try to put it in standard form. We'll just leave it like that in factored form. Okay. Now, real quick, I guess I'll kind of do this off to the side underneath here where I have some white space. So again, we're going to look at the function. The stuff on the inside is just u cubed. So let's say we started off with our function f of x being equal to u to the third power. Well, the derivative of the whole thing would just be 3 times u squared. And what we would do is, kind of off to the side, we would just take that expression and I would say, okay, well, u is equal to 4 minus x squared. So the derivative of u would be negative 2x to the first power. And at that point, we would go ahead and substitute it in there. And we would say, and I forgot here, this is supposed to be times u prime for the derivative of the whole thing using our chain rule. And now we can just kind of substitute our things back into it. So I would say 3 times, plug in the 4 minus the x squared quantity squared here, and then plug in the negative 2x for u prime, and we still wind up at the negative 6x times 4 minus x squared quantity squared. I don't want to do too much of the u substitution right now. I'm just, I'm laying groundwork for things that we will use u substitution for in the future. So for most of the examples, I'm going to just look at it as the derivative of the whole thing times the derivative of the inside, or vice versa. Derivative of the inside times derivative of the outside. So let's take a look here. What this is telling us, where we have some general exponent and power rules. Okay. Remember, if I have something as an exponent here, the power rule winds up getting placed in front, and we drop it by 1, and then we just take the derivative of whatever the inside bit is to get that. And it'll be the same thing if we're using e, because you remember, if you have something e to the x power, the derivative of e to the x power is itself. So when I take the derivative of this, when I have something as an exponent like this, we would be looking at, this whole thing where this bit is considered the inside. And so the whole thing stays the whole thing, and we multiply it by the derivative of the inside, which is where we have that g prime of x. So those are just some things to kind of keep in mind as we get into these. Now I'm going to do a couple of these here for you as an example, and then I would like you to, work a couple on your own just to see if you're, getting the hang of it. So let's change my colors here so not everything looks red. For each function, find the derivative. So this is a composite function. We have a radical function where we're taking the quadratic that's inside of it and cubing it. So what I'm going to do first here, really, personally, I don't like radicals when I try to do derivatives. I'm going to go ahead and convert this into an exponential form. And I'm going to go ahead and just change colors real quick. I'm not sure if that one's really going to be dark enough for people to see on their screen. So here I'm going to write it as x squared minus 1, and in this case it would be raised to the 3/2 power. So the derivative of the whole thing, let's do that one in green, the derivative of the whole thing, we'll just use our power rule here on that whole expression. And I will then take the derivative of the inside, which is just going to be this bit here, and see what we end up with. So let's go back to that kind of greenish color. So the derivative of the whole thing, using the power rule, will be 3/2 times x squared minus 1, and we subtract the exponent by 1, and so that's going to put me to the 1/2 power. So that's to the derivative of the whole thing. Now we take the derivative of just the inside bit, which would be 2x. And, you know, normally we could stop there if we were just trying to do like an arithmetic expression, but let's go ahead and put it back in kind of standard form, where we'll go ahead and multiply through some things. Oh, and I picked blue back here, didn't I? Because I thought that that other color, that grayish color, was going to be too light. So here, this 2 and this 2 will simplify to be 1. So I have 3 times x. This 3 will get multiplied to the remaining x here, so that'll give me 3x times, and you can either leave this in radical form, saying x squared minus 1, exponent form to the 1/2 power, or some people may prefer it to be 3x times the square root of x squared minus 1. Either one of those would be acceptable. Okay? So, I hope you're feeling okay with this. What I'm going to do now is I'm going to ask you guys to work out example B. Try working this one out on your own, see what you get. I'm going to pause the video here and work it out, and when I hit play again, you'll see the, the work there. But you go ahead and pause the video now, try working it out, and then hit play and see what I came up with. All right, so how did you do? I wound up with my final derivative of example B to be 28 divided by 2x minus 3 quantity cubed in the denominator. So I'm taking the first thing I did is I moved the expression from the denominator to the numerator so I could use the power rule. The power rule on the whole thing, the -2 exponent and the -7, gave me a product of a positive 14. And when I subtracted the exponent, we wound up with the quantity to the -3rd power. Take the derivative of the inside part, which I did in red. So the derivative of the inside is just 2. And the 2 and the 14 multiplied together to give me a 28. Move the negative exponent back to the denominator, and we're done. So hopefully we're getting the hang of it. Some of this is going to be a little bit easier than others. And again, on this one, this would be a perfect example for you to go ahead and try pausing the video again and work it out and see how you do. So I'm going to go ahead and pause it here, and when I am done, I'll hit play again. And again, you try working this one out on your own, see if you can identify the derivative using the chain rule. And when you're done, hit play and see how it looks with my answer. Okay, so hopefully you worked it out and you did what you were supposed to do. How did you do? I left the answer in 2 forms. Personally, I would have probably left it in this form here. I have a tendency to just leave things in exponential form, but you certainly could have changed the exponent back into a radical and done the cube root in the denominator. So let me just kind of walk you through. Again, the derivative of the whole thing, we're doing the power rule, where I multiply the 2/3 as my exponent, and we drop the exponent by 1 using the power rule. So that's where I have the kind of that orangish color of being 2/3 times 5 minus 4x squared raised to the power of negative 1/3. And then I take the derivative of the inside part, which is giving me a negative 8x. And then I just kind of multiply through and see what I get. So the negative 8x gets multiplied to the 2 in the numerator, giving me my negative 16x in the numerator. And I'm going to go ahead and just move the radical, the negative exponent to the denominator, and that's why I have a denominator of 3 times 5 minus 4x squared, quantity 1/3, raised to the 1/3 power. Now the next one I'm going to go ahead and do with you and kind of walk you through it, because this one is where we're kind of looking at using those exponent values, okay? So let's take a look here. So I'm going to say y prime. All right, I want to find the derivative of function y, and I'm going to look at it as from here to here. This is the derivative of the whole thing, okay? But inside of the exponent value, we have this expression. So I'm going to find the derivative. Let's see, get a color. I'm going to find also the derivative of this bit here. So that's going to be considered the inside expression. Well, the derivative of the whole thing is just what I have kind of bracketed in green, which would be e to the 3x squared power. That's the derivative of the whole thing. The derivative of the inside part, which is going to be what the 3x squared part is, that would be 6x. And really, you could stop there, although most people are probably going to want to write it a little bit more cleanly and say y prime would be equal to 6x times e to the 3x squared power. And there we go. That's how we're going to be looking at using the chain rule for that exponential expression. Now we have a couple more here, and again, example E, I think this is going to be a good one for you to again practice on your own. Go ahead and pause the video here and try working out the example, see what you're able to get. And then part F, I am going to do for you, so follow along with that one because that's going to introduce a repeated use of the chain rule. So pause the video now, work out E, and when you hit play again, the work that I have is going to kind of pop up here for you. Okay, so how did you do? I wound up with a derivative of 4 divided by 6x plus 3, quantity raised to the 4/3 power. So the derivative of the whole thing, we use the power rule. So the negative exponent and the negative 2 multiply together to give me the positive 2/3. Subtracting negative 1/3 by 1 gives me the exponent negative 4/3. So that's the derivative of the whole thing that's in blue. The derivative of the inside part I'm doing in green. So the derivative of 6x plus 3 is just 6. And now we wind up multiplying the terms outside. So the 3 and the 6 simplify to be just a 2. So 2 times 2 gives me 4 in the numerator. And I'm going to just move the negative exponent term to the denominator. And that's how I got 4 over 6x plus 3 raised to the 4/3 power. Now, the next one, this is where we're going to start introducing the idea of repeated use of the chain rule. Just like what we would see with derivatives in general, you can take more than one derivative of a function. L'Hopital's rule, you can use more than once at a time. You can have repeated uses of those, so we can have repeated uses of the chain rule as well. Now the first thing that I want to do on this one is this exponent of 3, a lot of times that kind of throws people off. So I'm going to rewrite the problem. And the way that I'm going to write it is I'm going to say cosine of e to the 5 theta power, and I'm going to have that raised to the whole thing raised to the 3rd power. That one makes a little bit more sense. Now, how are we going to use the chain rule multiple times? Well, let's go ahead and get some colors going here. The derivative of the whole thing is the whole quantity raised to the third power. So that's where we take the derivative of just the whole thing, the derivative of the outside part. Okay, well, I also have the derivative of the inside part, meaning just this bit here. And let me see if I can, let's move that down a little bit, just the cosine from cosine of e to the 5 theta power. But I also have this bit here, e to the 5 theta, that I could find the derivative of, and it, like what we saw in a recent example, has that bit inside of it that we can find the derivative of. And this is why I say sometimes it's easier to work from the inside out and unpack it. But I'll try to keep things working consistent here and keep taking the derivative of the outside and multiply it by whatever we had on the inside. So starting us off, let's get y prime. So starting us off is the derivative of the whole thing, which I'm going to do in black. The power rule for this one is simply going to be 3 times cosine of e to the 5 theta power. That's not 50, that's theta. Quantity squared. Now I'm going to take the derivative of the inside bit, which is just the cosine e to the 5 theta. Well, the derivative of cosine is going to be negative sine, so I'm going to get negative sine e to the 5 theta. Now we take the derivative of e to the 5 theta itself, and e to the 5 theta itself is just e to the 5 theta. And finally, we take the derivative of 5 theta, and theta in this case is just acting like x. So the derivative of 5 theta is 5. And that is the repeated use of the chain rule for this particular example. And you see repeated uses of chain rules a lot of times with trig stuff. So let's see if we can kind of simplify this a little bit. Let's go back to our purple color here for the overall derivative. So the stuff that's on the outside clearly is going to get multiplied together, but we have to take into account that we have a negative on the sign. So the 3 times the negative 1 on the sign times the 5 ultimately is going to give me negative 15. Okay. And here we're going to say, well, we have multiplied e to the 5 theta. And then we have, now cosine and sine, some people are going to just write it out the way that it's written, cosine, and some people insist on writing sine first. So it really doesn't make a difference which one you do. So here I'm going to just say sine because I imagine that that's probably how it would be written as like an example, an answer choice for a multiple choice question. I imagine sine would probably be written first. And oops, not O, cosine. And then we'll say cosine e to the 5 theta, and we're done. Now, let's see. I feel like I'm missing something here. Give me 1 second. Let me pause this. Let me double check something. I want to make sure I got this one right. Hold on. Okay, yeah, crisis averted. I don't know why it doesn't look right to me in my head, you know, looking at it on the board here, but this is definitely my derivative. So there's your first example of the repeated use of using the chain rule. And all right, let's continue on. And there's a lot to unpack in this lesson. We got quite a few practice problems to work out. Now, this one here, example G, I think this one would be a good example to use, like if you did want to attempt to use U substitution. Now, like I said, I showed you one example kind of at the beginning when we first introduced what the chain rule is. We will use U substitution for even more advanced derivative things that we're going to be doing at some point in our future lessons. So I think example G will be a perfect time to work a problem out using U substitution. Now, if you don't want to use U substitution, don't. Keep doing it the same way, and we should wind up with the same answers. So I'm going to look at the function here, function f, as being the natural log of u squared. Okay. So if I took just the derivative as it is, just looking at, the function as it is, I'm going to take, using the chain rule, I'm going to take the derivative of the whole thing times the derivative of the inside. Okay. Well, the derivative of the whole thing, so here we're going to say f prime of x, and I'm going to stop switching colors here, just, hopefully the colors help keep things organized. But the derivative of the whole thing, in this case, oh, I'm skipping a step because this is where we're getting into the realm of, not only do we want you to be a good calculus student, but we're going to make things, we're definitely going to throw some extra things at you just to make sure that you remember all of those primary lessons that you had from earlier math classes. And using the power rule for the exponent, we're going to put the 2 in front of the log. Now I'm going to, and I will go ahead and just change colors here just to indicate that I'm doing the derivative now. So I'm going to say f prime of x. Well, according to our chain rule, the derivative of the whole thing is going to be 2 over u, according to the log derivative. And the derivative of the inside part is going to be u prime. Or you could write it as 2u prime over u, whichever makes more sense to you. Now, this is what we do in U substitution, is we just kind of have an aside. We are going to say, okay, well, I'm going to just take this and say, all right, well, off to the side somewhere, we're going to say U, in this case, is all of the stuff that's inside of this parenthesis. That is what we're looking at as U. So U was the x squared plus x plus 1. So that means U prime would be 2x plus 1. And so at this point, we have that U substitution where we did the derivative of the inside part off to the side. And, now we can just kind of go back and do our, substitute those things into what we have for the derivative of function f. And let's see, can I move this guy down a little bit? I sure can. Haha. So we'll keep things just kind of going down. All right, and make sure I'm using my green color. I am. So I'm going to say, again, we're just still doing f prime of x. So I'm going to say 2 times u prime, which in this case was 2x plus 1, just substituting it back in, over u, which in this case is going to be the x squared plus x plus 1. And there is the derivative. So this one is one that I wanted to do with U substitution because I think the polynomial lended itself well to doing it. And if you did, not using U substitution, you should have wound up, with the same thing. Now for this next one here, we're getting back into, this is I have a problem with questions like this because this particular question is intentionally written not to test your ability to use the chain rule, but to see, okay, well, let's mess with them and see just how complicated we can make something and make them still be able to do something. In this case, where we might have to use some product rule or something else that we've done. Okay. This whole thing, this bit right here is what I'm looking at. That's where I'm having an issue. Because you're probably going to look at that and say, okay, well, maybe I got to use the product rule because a lot of people do have a tendency to forget that E is a number. But this stuff that I have in boxed in blue, they've intentionally written that more complicated than it really needs to be. Okay, so looking at this bit here, the exponent, the 4 times the natural log of x, we can rewrite that whole thing that's in blue as e to the natural log of x to the 4th power, or negative 4th power. I didn't get my negative sign there very well. Excuse me. Natural log of x to the negative 4th power. Well, if you go to your calculator and if you just type in e to the natural log of x to the negative 4th power, just e to the natural log of x like this, these undo each other. And all you're left with is this bit here, x to the negative 4th. So really, function f should have been written as x squared multiplied to x to the negative 4th. Or maybe x squared over x to the negative 4th. Okay? Which, either way that you do this, that is simply going to be x to the negative 2 power that we're going to wind up taking the derivative of. So I wind up here, negative 2 x to the negative 3rd power. Ooh, that was a terrible 3. My arm spasmed or something. And so we'll just move the negative exponent to the denominator, giving me negative 2 over x to the 3rd power. So this one doesn't require any kind of use of the chain rule or product rule or anything like that. And it bugs me that sometimes math curriculums and test writers, they go to this crazy length of say, let's see if they remember all their log properties and just mess with them. This was a much more complicated question than it really needed to be, and probably doesn't really belong here. But since it's in our notes, we'll go ahead and do it. Now here, this one is going to be a very good use of incorporating prior skills. This one is definitely going to use the chain rule. And it's also going to, I don't think this is, maybe it's going to incorporate the product rule. We'll take a look and see. So taking a look, we're definitely going to, I think it's worthwhile to go ahead and just say, well, let's take our function and let's make it a little bit more understandable. If you need to, you don't need to do this, but I'm going to say cosine of 4x quantity squared minus sine of 4x quantity squared, because that makes it, to me, visually, my mind just processes it a little bit better when it's written that way. Now, again, I'm going to attempt to avoid switching colors here. So the derivative of the whole thing is just going to be 2 times cosine of 4x to the 1st power. And the derivative of the initial inside part being cosine of 4x, would be negative sine of 4x. But we also have the 4x that's going to be considered an inside part. Okay, and you're more than welcome to just break these apart and just look at them one at a time. You don't have to do them in one whole shot like I'm going to do here. So the derivative of the 4x on the final inside part is going to be 4. So that is the derivative of just the first part, cosine of 4x raised to the second power. Now we have to do the same thing with the sine of 4x raised to the second power. Now in this case, we are subtracting all of that expression. So anything that I take the derivative of, I want to keep it in its own set of parentheses. So again, just using the power rule on that expression, we're going to get 2 times sine of 4x to the first power. And now we look at the inside part. The sine of 4x itself, the derivative of that, is going to be cosine of 4x. And then we take a look at its inside part, the 4x again, and we get another 4 when I take the derivative of 4x. Okay. And now let's just see what we wind up getting. So the 2, we're taking a look at the term on the left. 2 times the negative on the sine times the 4 is going to give me negative 8. And again, there's no standard way of writing cosine or sine, but I do think more curriculums are going to write sine before they write cosine. So I'm going to say negative 8 times sine of 4x times cosine of 4x. And here we're going to subtract. So the 2 times the 4 inside of the parentheses is just going to be 8. Distribute the negative, and that'll be another negative 8. And again, we'll keep sine written first. No particular reason that it needs to be. Sine of 4x times cosine of 4x. And well, if you notice, these are like terms. Sine of 4x, cosine of 4x, everything is the same from one term to the next. So we're going to just combine them, and that'll be negative 16 times sine of 4x times cosine of 4x. And there we go. The next one is definitely going to incorporate the product rule because we clearly have 2x terms at some point that are going to wind up getting multiplied together. So here, y, I'm going to just write it like this, x to the 4th power times sine of sine of x quantity squared. So here we're going to use our normal, we do have to use our product rule here, which, you remember the product rule would be f prime times g plus f times g prime. Okay. So I'm going to take the derivative of the x to the 4th power, and that'll give me 3x, and it's going to get multiplied to sine of x quantity squared. And now we have to use the product rule, so we're going to leave x to the 4th by itself now, so it stays x to the 4th. And I'm going to take the derivative of the sine of x squared. Well, the sine of x squared, let's just kind of uncomplicate it a little bit. Let's just get it over here off to the side. We have to use, the chain rule. So the sine of x squared, using the overall power rule on the whole thing, would be 2 times the sine of x to the 1st power. But then I have to take the derivative of the inside part, and the derivative of sine is going to be cosine. So that's going to wind up being what x to the 4th gets multiplied to. So that's going to get multiplied 2 times sine of x times cosine of x. And let's work through and see what we wind up with for our final expression. Okay. And some of you are probably having a hissy fit right now because I am apparently asleep at the wheel here on this bit here. The derivative of x to the fourth is not 3x. Rather, it is 4 times x to the third power. There we go. Now, I know what I'm doing, I swear. Trust me. Now, for the stuff that we see on the left, the 4x to the third power times sine of, x squared, those aren't really going to simplify. So you could probably leave it as it's written. However, convention is probably going to write, like, if, again, thinking in terms of a multiple choice answer, it's probably going to be written like this times sine squared of x, like that. And on the right side, we can multiply through a little bit. We can multiply the 2 to the x to the fourth. So that would be 2x to the fourth times sine of x times the cosine of x. And let's see, we do have some like terms that we could, take out. So again, numerically, this is where I would stop for sure on a free response question. But again, thinking in terms of a multiple choice question, we do have a greatest common factor of 2x cubed and sine of x. So I can factor out a 2x cubed sine of x as a greatest common factor. And if I do, the first term is going to just be 2 times the sine of x. And the second term would be plus 1x cosine of x. So this would be the final simplified derivative that you would expect to see as a kind of a multiple choice type answer. All right, so ideally at the initial outset of the lesson, hopefully you were understanding that, oh, the chain rule is not so bad, but you start throwing in there with some of the other properties of derivatives, like logarithms and exponents and like e to the x power kind of stuff and product rules. And, at some point we're probably going to see something with a quotient rule. Let's see how that goes. And all right. So looking at this one, I want you to go ahead and try pausing the video on both of these and just see how you do. Work out K and L on your own. And when you're done, I'll have the answers put up here for you just to see what we got. All right, so here are the answers for K and L. Hopefully you are in agreement with the final derivative expressions that I got. Looking at the one on the left in blue, the derivative of the whole thing would be 1 over natural log of x. The derivative of natural log of x on the inside is just 1 over x. Multiply those two terms together, 1 over x times natural log of x. L in red on the right. Here we're going to have repeated uses of the chain rule. The derivative of the whole thing is cosine e to the pi x power. The derivative of the initial inside piece, which is the e to the pi x power, is the derivative e to the pi x power. And then finally we have the derivative of pi times x, which would just be pi. So when we multiply them together, normal convention would probably write it as pi times e to the pi x power times cosine of e to the pi x power. All right, I know we're getting long on time, guys, and I apologize. This isn't my intention to kill you guys with this stuff, but we need to have some good looks at these things. And here, again, I'm going to ask you guys to go ahead and just for the answers of time, maybe save some time on the video, go ahead and try working example M and N on your own, and then hit play and see how your answers look compared to mine. All right, so here are the results of the last two numeric derivatives that we're going to be taking a look at. The one on the left Again, I'm just going to rewrite the cosine squared in its own parentheses squared. So the derivative of the whole thing will give me 8 times cosine pi theta. The derivative of the inside part, which is the entire cosine pi theta, is the negative sine pi theta. And the derivative of the final inside term would be the derivative of pi theta, which would just be pi. So we wind up with negative 8 pi sine pi theta times cosine pi theta. The last one, I'm going to begin by writing it in exponential form. So the tangent of square root of 2x minus 3 is just going to be tangent of 2x minus 3 raised to the 1/2 power. So the derivative of the whole thing would just be secant squared of that expression. And then we look at the derivative of the initial inside part, which is the whole, like the square root, the 2x minus 3 to the 1/2 power. So we use the power rule on that expression, and then we take the derivative of the 2x minus 3, which is going to give me a 2. The 1/2 and the 2 simplify, move the negative exponent to the denominator. And just to simplify things in this case, so I don't have to have 2 sets of parentheses on the secant, I'm just putting it back in radical form of secant squared radical 2x minus 3 over radical 2x minus 3. Man, I know, I'm sorry, this has been a long lesson. I sincerely apologize, but the last thing we're going to be taking a look at here is kind of a symbolic use of the chain rule, where we're going to be looking at it in terms of a table. So they're telling us in this example, f is going to be a continuous and differentiable function on the interval from 0 to 1. And it's telling us that g of x is going to be equal to f of 4x, and the values of f prime of x are given to you. So find the value of g prime of 0.2. So the way that I'm going to look at this here is initially is I'm going to be thinking that, well, g prime of x must be equal to the derivative of using the chain rule on this bit here would give me 4 times f prime of 4x. So that's what I'm going to get when I take the chain rule and take the derivative of the f of 4x to get the expression for g prime of x. So here we're going to say g prime of x is equal to, again, the 4 times the f prime of 4x. And in this case, we're looking at it in terms of, 0.2. It says we'll find g of 0.2, or g prime of 0.2. So 0.2. So I have 4 times f prime of 4 times 0.2. And that will give me 4 times f prime of 0.8. And f prime of 0.8 is given to me from the table to be 1.125. So we get 4 times 1.125. And here I would just go to my calculator. I'm not going to try and do that by hand. And we're going to wind up with 4.5. So now let's take a look at example 5, where we have this new table. And it's giving us a variety of values. They're giving us 3 input numbers, function f and its derivative values, function g and its derivative values. And in part A, find the equation of the tangent line to x equals -1 if h of x is equal to 3 times f of g of x. Okay? So according to the chain rule, here, h prime of x would be equal to 3 times f prime of g of x times g prime of x. the derivative of the whole thing times the derivative of the inside. And in this case, we're looking at it when x is a -1. So we might have to scroll back up to see the numbers here in a minute, but we're looking at this case of h prime of, what was it, -1. So here I'm going to say 3 times f prime of g of 1, -1, times g, I don't need the parenthesis here, times g prime of -1. So let's see what we get from our table. Well, g of -1, g of -1 is -1, and g prime of -1 is 2. So let's go substitute those numbers into our problem. So that'll be 3 times, so g prime of -1 is -1, so I'll get f prime of -1 now. And g prime of -1 was 2. So here we can go ahead and multiply the 3 and the 2 together, and that'll be 6 times, and so now we need to figure out, well, what is f prime of -1? So f prime of -1 is a 4. So that'll be 4. So the derivative of the function at x is equal to -1 is 24, meaning that is the value that I'm going to use for my slope, because we're trying to write the equation of a line tangent to the function given what we know. Now the one thing is they gave us the value of x for the function, but they're not giving us the y value, and we can't see it in the table either. So I'm going to have to figure out what is h of -1. So h of -1 will be equal to 3 times function f of g of -1, and see what we end up with. So f, g of -1, g of -1 was -1. Okay, so we know that one, -1. So that'll give me 3 times f of -1. So f of -1 in this case is a -2. So I get 3 times -2. So my y value is -6. So when x is -1, y is -6. So the equation of the tangent line would be y is equal to 24 times x plus 1 minus 6. And the last one, let's see, it's not really giving us we're not looking at the table anymore for this particular function, no, that is. We're still having to go back and look at it. So let me see if I can copy the table over here real quick. Give me 1 second. All right, I got a table here, so that'll make it a little easier instead of having to jump back and forth between 2 different screens. So this is our last example. J of x is equal to the composite function f of g of x times cosine of x, and it's asking us what is the derivative of the function at 0. So we have a composite function, so we're using the chain rule, and we're multiplying 2 functions together, or we're multiplying the composite to another function, so we're definitely using the product rule at the same time. So let's see what we're able to get here. So we'll say j prime of x. So the derivative of the first part, we have to use the chain rule on, so I'm going to say f prime of g of x times g prime of x times the cosine of x. And now we're going to add the composite f of g of x times the derivative of cosine, which would be negative sine of x. And now that we have an expression for the derivative, now we can start plugging in our value and start simplifying it. So now we'll say g prime of 0. So f prime of g of 0 times g prime of 0 times cosine of 0 plus f of g of 0 times negative sine of 0. And let's see what we end up with here. So g of 0, going to our table, g of 0 is a 2. G prime of 0 is going to be a negative 3. And cosine of 0 is 1. So let's keep going. F of g of 0 will give me g of 0 is 2. And negative sine of 0 is 0. So this whole thing goes away. We don't need to worry about it anymore. Anything times 0 is 0. So here we're going to have negative 3 times f prime of, well, I don't need to write f prime of 2. We can just plug in that number. What is f prime of 2 according to the table? F prime of 2 according to the table is a negative 2. So j prime of 0 is a positive 6. And that, ladies and gentlemen, is going to bring us to the conclusion of this very extensive lesson on the chain rule. I very much appreciate your patience, and I hope I was able to work the problems out to where any questions that you may have had would have been answered by the work. But if not, by all means, get in touch with me. Let me know how I can help. And until I see you guys in class again, thanks for watching. Take care of yourselves, be good to each other, and we'll see you again soon.